Hey, Jesse, how you doing? Good to see you here today. What are we working on? Get started on some work here, some Pearson, probably. We got the test coming up. Office hours, March 30th. Got the notes, loading up my Pearson. Mubot's awake right there, ready to go. Signing in. What did we work on? Got last assignments, right? And some classes have them do a little bit later, but the reason I didn't put them due, I think some people put it due on day of the test. People don't do the work when it's due on the day of the test. If you put the work due on the day of the test, it doesn't get done. I know that. Anything help to prepare for the test? Yeah, we can talk about the test right here. Look at managing completes real quick. Talk about the test, the upcoming test. A lot of people did the work yesterday, but it's interesting to me because it's due on the 31st tomorrow, but there's like 250 people. So only like 90 people took the quiz. That's from the morning class where more people attend. And I'm just like, like a bunch of people are going to get to the quiz tomorrow and just be like, I got no idea. And dang it. Well, that's what we do. We do work. All right, let's talk about the test right here. The test. Okay, let's take a look at the test topics. Okay. Nice job, Jesse, right there. So this is preparing for the Stat 201 test. Stat 201, preparing for test 2. Okay, if you're watching this about preparing for test 2, the first thing you should know is Mubot's putting a link right here for review 2 right now. So you need to check out the review 2 page. Now, the reason I say check out the review 2 page is because there's a ton of videos. You may not know this. Mubot's got the link in the chat. Just look over there at the chat, or these are all connected to the Canvas page under stat201.utk.edu. We have that URL also. You can see here the exams, review 2 material exam 2. Boom, you're here. And so when you go here, you've got a lot of files to look at, but you've also got review videos going over different chapters. You've got chapter 7, chapter 8, probability and sampling distributions right there. So there's all the material. You've got review questions from the test right here. All these different review questions to throw some points in the chat. Lots of different stuff covered. And then you've got speed runs right here of different topics where I kind of go over very concisely the topics. So if you're wanting to go over chapter 7, really good chapter to review.
Epic Stat 201 speed runs of statistics. Brian Stevens versus Chapter 7, Linear Regression. Begin.
Let's start with, so you can see what we're covering there in the top corner. Conditions for regression, QQ straight enough, no outliers, plot doesn't thicken. Least squares line, which minimizes the residuals. All these things right here are the topics that you should know, like the actual and the predicted, estimate y given an x, and you can just see the different topics as I go through. So what I did here, and I thought it would help, is highlighting the different things right there as we're doing it, so you can talk about the different topics. So there's residual plots right here, all this good stuff. There's a ton to cover. There's so much to cover that I really can't cover it all right now, but I can cover any specific things. So you can always come in here and say, hey, Brian, can you go over this more in depth? Can you speak specifically about, what are the conditions for regression? What does it mean for a residual plot to be good? All these different things right here. Now, I guess one thing, so that's kind of your basics on review, but there are interpretation questions. Let's put this right here. Interpretation questions on test 2. So these are the ones people usually get not enough points on. We're going to load up Jump right here and talk about how to do interpretations for test 2. So these are the ones people just forget how to interpret. I need to download the new Jump because I keep on having to open my license file. It's like, where's your license file? Where is the license file? Oh no, there's Jump license file. That can work, right? Oh no, I never saved it. So Jesse, do you remember how to interpret the slope, the intercept, the r squared, all that good stuff right there? Let's go here and do some slope, intercept, r squared interpretations. So when we do regression, we need to know what the output looks like. And what's really great about doing a regression is you kind of have to know the conditions for regression. The first condition for regression is QQ, which is two quantitative variables. So we have fit y by x right here. With fit y by x, you need two quantitative variables. I can actually narrow this down by removing the characters and only have the quantitative variables right here. So let's look right here at how many hours somebody sleeps a night. And let's do the longest they've been awake. So we asked somebody, what's the longest amount of time you've been awake? There's probably some answers we could remove here because I think some people said like 0 hours, which means the longest you've been awake is 0 hours, like continuous. I think some people said like 80 hours. There's world records of like 100 hours, I think, but don't do that. You need to get your 8 hours of sleep a night. Really helps your body. So that was the first question. How long have you been awake consecutively? And then the other question is, how many hours of night do you get? How many hours of sleep do you get a night generally? So that's the other question right there. So we're seeing if the longest someone has been awake consecutively explains how many hours of night of sleep they get. And if you notice here, there's actually a problem with the regression. There's two problems, I would say. Can you spot the two problems with the regression? So Jesse, if you're watching right here, what are the two problems? One of them is a little more obvious than another. There's two problems with the regression, I would say. Hey, Garen, good to see you. Yeah! Congratulations, Garen. Thank you so much. I remember your picture right there, and I think I remember your name too. Thank you so much. I appreciate that so much. Your favorite class at UT? Thank you. That makes my day hearing that. We're talking about some regression right now. Garen, you just got everyone 100 points watching right here. I appreciate that so much. Thank you, and congratulations on graduating. Look at Jesse just right there earning everyone another 100 points. Garen, yeah, I remember your picture. I'm like, I remember that. Well, congratulations, and I'll be back at UT in the fall, like in person. So swing by, say hey, be like, hey, Brian, I'm Garen. I'll be like, hey, what's up? So, awesome. And Jesse's seeing those outliers right there. Great job. Yeah, congratulations. That's really great to hear. I'd love graduating. Awesome. Any tips for the class? Jesse, you're doing great. You got all the tips. Do the work. I don't know. You're doing great. So Garen, drop some tips if you like. Look right here. You identified it, Jesse. Outlier at 48. And you literally said both perfectly. It's outlier and it is curved. You can actually look for curvature by fitting the like the one right here. You see the small bend. I guess the bend's not as big as I thought it was, but there's a little bit of a bend, maybe due to that. But yeah, we fit a polynomial, which we don't do in this class. But you got it, Jesse. You were 100% right. There's outliers, especially right there. That big outlier right there. Did you say 48 on the dot? You said at like 48. Literally at 48x. You were perfectly on it. That's the biggest outlier. The other ones there's some moderate outliers, but that's the biggest outlier. So we have a huge outlier, little bit of a curvature. Probably the big outlier is the one to immediately catch right there. Like that's the obvious one. And what's nice is we can do things in Jump where we can mark it with colors and stuff like this. So we can make it red, and we could do a marker right here, make it a star to make it a little more obvious when we're presenting data to somebody. There we go. Yeah, well, that's Garen. Garen, 100 points. Garen's right. Practice and just learn how to interpret these things, because the R squared is actually what I think the easiest one to interpret. So let's take this data right here. We're going to bring it over. We got it here. So we're going to take it over. We're going to take this picture over. Okay, so we have the R squared. Okay, let's bring it over to a new screen. So Jesse, I want you to try to write these out. I want you to interpret the R squared here in a moment to see if you remember how to do it. I'll write the blank interpretations again here in a moment, but I want you to try to interpret the R squared. So this is kind of a review of regression, and as Garen said right there, it really comes down to practice, practice, practice. So what is the R squared interpretation? So R squared right here. Now, a common mistake people have is that they think R is R squared, but they're not. R squared is R squared. R is not R squared. R is correlation. So that's what that is. And this is percent of variation. So that's a reminder right there on what R squared is. It deals with percent of variation. And we often take this number right here and times it by 100. So this number right here is a percent of variation, so we usually multiply it by 100. And so when you do the interpretation of r squared, you're looking at an interpretation like I'm off the screen. Sure. I guess we are at the bottom of this document. There we go. So we're looking at blank. Yeah, 6.34% of the variation nightly hours to explained by the variation in logs. Boom, Jesse, 100%. Yep. Jesse did it perfectly right there. R squared, which is blank percent of the variation in Y, is explained. And you think about the X is explained by the variation in X. And there it is right there. That is literally it. So Jesse said 6.3% of the variation, and we'll pin the comma right there. 6.3% of the variation in hours of nightly sleep, which is Y. So take a look as we do this right here. I'll circle it, or I'll highlight it. So Jesse said 6.3% of the variation in hours of nightly sleep is explained by the longest hours someone is awake, and by the variation in the longest hours awake. And that's got it right there. That is the perfect answers, Jesse. And so if the graders took off any points for that, I'd be like, nope, we are giving you all those points. You have earned those points. So I like to say explained by, because then you can remember the X's are the ones explaining. It helps you with the remembering how to say it. Like blank percent of the variation in Y is explained by the variation in X. So the X is doing the explaining of it. That is, yeah, exactly. That's the easiest way to create like a mnemonic to remember the explain, the X explains. Now we get here to the coefficient of the intercept, and the coefficient of the intercept is right here in the equation. Now the equation is y hat equals b0 plus b1x. And so when you look at this equation over here, this is the b0, and that is the estimate of the intercept. So when x is equal to 0, we expect y to equal b0. Oh my gosh. And this is the interpretation right here. So how would we interpret this value? So try to do this, and this is what we need to remember. So how would we do this? When x is equal to 0, we expect y to equal b0. So I'll zoom in. We don't really need the graphic up there anymore. When x is equal to 0, we expect y to equal b0. I guess we might want to look at that x and that y. That's the value of y right there, because this is the predicted hours of nightly sleep. And then you want to say expect, you don't want to say will. And then you could add in on, just in case other teachers are watching, on average. Sometimes people throw in that little on average. Oh, I like this. When longest hours, oh yeah, Jesse, 100 points. Comment if logical. So Jesse remembered right here. Jesse remembering even better. We usually comment on if it's logical or illogical. So when longest hours awake is equal to 0, we expect nightly hours of sleep to be equal to 7.30. I don't really care if it's on average because it's expect. You don't want to say will though, because that implies certainty. This would be illogical. This would be illogical as you cannot be awake for 0 hours, like the longest you've been awake. So the longest someone has been awake could not really be 0 hours, because we're saying the longest you've been awake is 0 hours. And someone said they reported that, so it doesn't really make sense. We can't talk about the longest I've been awake is 0 hours. That doesn't make sense. So the intercept is illogical, because when you think about it, if you're wondering why is it illogical, a lot of people say like, well, wait a minute, why is that illogical? Imagine we were to say here, let's predict somebody's, how many, let's say, this is kind of a weird one. Okay. Here's another intercept, Jesse, to interpret. So this intercept right here is a value of 46. But the value is for a what? So think about what this intercept is for as a value. So there's the intercept over there at 46. And so what is that intercept predicting for? Think about, because it's for age. When age is equal to 0, so what are we talking about right there? So when age is equal to 0, we expect somebody's class text to be equal to 46.11. So there's the value of the intercept. When age is equal to 0, we expect classroom text to be equal to 46.11. You can see it mathematically over there. Don't be tricked. Sometimes people think the intercept is just where it hits. It is when x is equal to 0. Just sometimes graphically it's not shown to you just because the data doesn't go there. This is an extrapolation of the model, which is another topic. So with this model, this would be predicting for a newborn baby. When age is equal to 0, we would expect class text equal 46.11 on average. This would be logical. Exactly. This is illogical because you cannot text when you're 0 years old. 100 points, Jesse. These are the exact answers we'd be looking for on the test when we ask you to interpret the intercept. It's important to remember the intercept is the first value, which is B0 right here. So that is the B0, and it's usually plus B1x, but this one has a negative slope, and this is the B1 value, and then this is times x right here. And those values are down lower, but this is the value of y right here. So y and technically y hat, because it's the predicted y value. The predicted y equals the intercept plus the slope coefficient times the x variable. There's the intercept's value. There is the slope value, and there is the x variable's name. So knowing these values is very important, and that brings us back to our original problem right here. And now we need to interpret the slope. So let's see right here. Interpret the slope. So for each 1 unit increase in x, we expect y to increase / decrease by b1 on average. So for each 1 unit increase in x, we expect y to increase or decrease by b1 on average. And there it is right there. So when we do this one right here, we have to know where we're talking about. The estimate of the slope is this. Now this means we're going for decrease because it's negative. And so the x variable's name is this. And the y variable, go for blue. The y variable is up here. And the y variable is hours of nightly sleep. For each 1 unit increase in the longest hours someone is awake, we expect hours of nightly sleep to decrease by 0.081 on average. There we go. And so Jesse, I think there's 12 points on the test. I feel like when you get to the test, you'll just do great on these because it really comes down to practice. And we have the r squared, we have the intercept. So here's the r squared. We'll write next to it. So this is the r squared. This is the intercept. And this is the slope. And really, with this practice right here, you're good to go. That is the practice you need. This is the ability you need to have to interpret these. We could look at the other one. The other one was on the predicting somebody's classroom text. So it's pretty interesting. It actually has a, it's not statistically significant though. Ooh, so that's the statistical significance of the model right there is the p-value of the slope. And the slope is not, even though you might say that looks like a strong slope. Apparently it's not. There could be. So statistical significance is when the p-value is below 0.05. This p-value here is not below 0.05, meaning that the slope is not statistically significant. You have to be careful because each sort of statistical significance, one, it means what we saw is unlikely by random chance, but you have to think about what does it mean in the context of this test. This test assumes that there is no slope, and the slope we observe is likely by random chance, meaning that there is not a slope that is significant significantly different from zero. So once again, you can go for the memorization on this. First, I would do memorization. Memorization would say, when we are looking at a model, a regression model, to see if it is statistically significant, we look at the slope. And remember, the age variable is the x variable, which is the slope. The other one's the intercept. So the slope here is not statistically significant, which means there is probably no relationship. Any relationship we see is likely by random chance. And so I could go a little more in depth on this. Go over here to R, and we can actually do a regression by random chance. So these right here, Jesse, are all random x's and random y's. So these are random normal numbers. And now I'm making a linear model. And check this out. If I were to plot these models, most of these lines would be very what? All of these are random chance models. So all of these are random chance models. And if you look at the red line, most of these red lines are very flat. We could even make a summary. And the p-value, which is also down here, is very high. A lot of these have p-values that are very high. This one's about the flattest it could be. And you see the flatter it is, the higher the p-value. I wish we could get a p-value of 1. It'd have to be no relationship at all. That one was actually statistically significant. You see that one's also flat. I'm trying to get the highest p-value. Let's get above 0.94. Above 0.94. Oh, there we go, 0.96. And that's the flattest one we see right there. And so when there is less statistical significance in the regression line, the p-value is even higher. Now we could contrast this where the y value is an equation of the x, where it's like x times 2 plus some random normal numbers. There we go. Now the x and the y are of an equation. If you notice, now it is statistically significant. This p-value here is a very, very tiny p-value, and this is to contrast the previous example where it was not statistically significant. This is a not statistically significant line. The intercept is not significant, but that doesn't matter, and so that means the intercept could be 0. It really doesn't matter, but we care more about the slope of the line, and we have evidence the slope of the line is not 0. So, okay, so for that, we would say since the p-value is not below 0.05, we have no evidence of a statistically... Yep. So this one right here, since the p-value is not below 0.05 for the slope, we do not have evidence of a significant relationship between x and y, statistically significant relationship between x and y, literally x and y. For this one, since the p-value of the slope, make sure it's of the slope variable, which is the second one. Since the p-value of the slope is below 0.05, we have evidence of a statistically significant relationship between x and y. We could put real variables in here, do something like the horsepower of a car related to the weight. So now this is a data set I have with cars right here, where we can look at the horsepower of a car related to the weight of a car. And actually, we can just copy, paste, beauty of coding. And so this is actually a statistically significant model here. What do you notice is going on in the middle of this model, Jesse? What is going on in the middle of this model? So this is statistically significant. But what's going on in the middle of this model? A little bit of what-ish. It might be outliers. It could also be plot thickening. It might be outliers or it could be plot thickening. So plot thickening is when we see uneven sort of... We could look at the residual plot too. So a little bit of plot thickening. You can actually just go here to plot the residuals. No, we don't want that. Plot the residuals of the model. And that's not exactly how I want to do it. And here's the residual plot over here. So the residual plot, which we can get in jump also, is basically the line flat. Don't look at that line over there. I'll bring up the other line again. A residual plot is basically the line flat. So there's your line, and there's the line flat. Does that make sense, Jesse? And if you look at the middle of this, do you see how the middle over here has this sort of like expanding to where the start has this, and then those 3 points below the line at the end? Yep. So those 3 points, those 1, 2, 3, the line is now here a flat line because anything on the line would have a residual of 0. And so there's been a really big review of regression right here. Just seeing that there is a little bit of plot thickening. And you know what? We actually don't have a problem with that condition. I won't get into the p-values over here. These are different p-values for different tests. The problem with this is actually the normality of the residuals is saying maybe this QQ plot for normality is not too good right there. So there's the normality plot. And actually, Jesse, 100 points, you were actually right. It's registering those more as outliers, that these observed values are much higher than we would have expected given the normal. So 1, 2, 3, 4, 5-ish, 1, 2, 3, 4, 5, maybe 6. There, it's saying these points around here are outliers. So you did really well because it actually, it's not saying we have a plot thickening issue via the test right there. It's saying these might be outliers. So that came back as the issue. So good job. And yeah, and then the QQ plot or the normality plot, which we talked about in Stat 201, actually shows it too with these points over here at the high end not following the normal. So yeah, and if you notice, this is 320 right here. This is how we do it in 320. We can make some really good plots. Where did I make those? I made the really nice plots yesterday. I'm looking for my GG. Oh, it is right here. So this is where we were doing it yesterday, and we made the nice plots. So yeah. Oh, I got to show these today in class. We got lab today coming up. But we made some much better plots. Oh, there it was. No, undefined column selected. Oh, because I think I created it down there. Normal quantile plot, and then you can actually hover over it. So there's my normal quantile plot. I use different variables, but you can actually see the values and what they are. So this is an interactive plot we can create here in R. You can put it into different websites or whatever. You can augment the size of it. You can even like zoom in on it, and then you can hover over it to get the points, which is kind of nice. So it's pretty cool. You can see how far away something is. I wish you could just measure that. Does it not have like a ruler measurement? I thought it did. But this is the advanced sort. Yeah, it is. And it's not that hard to do. It's what we do in 320. So yeah, and this is the same sort of thing you could get here in Jump, where you could go like normal quantile plot. Does not let you get that on this. You have to go here to distribution. Well, I guess you'd have to do this. You'd have to go here. You'd have to save the residuals. And then you have to go here. And then you have to go to distribution of the residuals. So we saved our residuals from the model. There's the residuals. And then you would go here. Yeah, they're skewed. Look at those skewed residuals. And then you would go to normal quantile plot. Oof, look at that. There's the normal quantile plot of the residuals. So if you look at this, this is a normal quantile plot. And so is this over here. And preferably, I like the normal quantile plot I've made over here with the text and the hover over abilities. But you can do the same sort of things in Jump. Jump's more of a classical looking statistical thing, where R is going to be more like the fun, neat things you can do, and you can easily change like your colors and everything nice and easily here. There's the one where I was doing this right here. We could just go green. Is that not? Oh, I saved it into P. So there we go. Yay! Now it's green. Yeah, nice and easy. What else, Jesse? What are you thinking about? What other topics are you wondering about? What other topics are you wondering about? That was a big review of regression right there. But what other topics are you thinking about? Anything you want to review, let me know. Let's see. Hey. We got Easter coming up. Exciting times. I'm back over to the main screen. I'm going to post the 320 assignment. 320 assignment. Okay. Assignments fall 320. Some probability. Yeah, let's do probability next. Do a good review of probability. Post the duplicate. Post their lab for today. And week 9 lab. Holy mackerel. Multiple regression part 1. Okay. There we go. Submit and publish. Okay. Good to go. Let's do some probability. Reviewing probability. And yeah, let's put that regression right there. Labeling the video for regression interpretation. Stat 201, probability, or yeah, review. Okay, let's do it. Here we are with some probability review. So some key terms you should know are going to be, actually let's make a grid for it. I would highly suggest writing down this grid I'm about to make. So we have the rule, we have the word, we have the condition, and we have the math. Okay. So we have a word, a rule, and condition and mathematics associated with it. Okay, so what are any of the rules we have, like the major rules? There's a lot of rules, but what are some of the major rules that we talk about? The first rule, probability, is all probabilities are contained between 0 and 1. So, if you're talking about probabilities or even p or p values like proportions, they have to be between 0 and 1. So that's a good check on, am I talking about p hat? Well, is it between 0 and 1? Oh, it's like 50. Well, I'm talking 50%. So there's a lot of ways we can check and make sure we have things correct, especially with notation. So one of the big rules on probability is the multiplication rule. We also have the addition rule. We also have the complement rule. So these are different rules right here, which we can use. Addition, multiplication, and the complement. The other things we're missing for rules right now are rule number 1, which is probabilities are between 0 and 1. And rule number 2, the set of all probabilities adds up to 1. So if you have like someone can make an A, B, C, D, or F in a class, well, that means if they've got a grade, they can also withdraw from a class. If you label everything that could occur, it would need to have all probabilities add up to 1 as disjoint events, which we'll talk about what disjoint means here in a second. So the word for multiplication that we use is and, addition is or, complement is not. The condition for multiplication is going to be independent. There are ways to multiply things. Great job, Jesse, right there. Yep. There are ways to multiply things that are not independent. You just have to have the new probabilities based on the dependency. We go for easier sort of mathematics here, so we don't make it too complicated. Yep, disjoint, which is also the same thing as mutually exclusive. I'll expand on that here in a moment. Complement. They have to be disjoint, but really, you just say something is not this. It's either this or not this. For the mathematics, thought I hit the right button right there. For the mathematics, we have multiplication is simply multiply A, or we'll say probability of A times probability of B. For addition, it's just like you would think it is. It's probability of A plus probability of B. And then for the complement, it's going to be probability of not A is equal to 1 minus probability of A. And this is the probability of A or B, probability of A and B. Very important to see the words right here and how they're associated. So a lot of confusion usually arises between the following. These words. This is where most of the confusion takes place. So I want you to understand how to check if something is independent. Independent means if I know A happened, it tells me nothing about B happening. And vice versa. If you know B happens, it tells you nothing about A. Well, is B independent of A? Is A independent of B? So things like that. Like school being off would be dependent on snow, but snow would not be dependent on school being off. Like it's not more likely to snow if school is off, like if they cancel school. Well, but you could say if you know school is canceled, is it more likely it snowed? But it wouldn't influence the snow. It just might change the probability if we didn't know it. It's like, well, school's canceled today. Is it snowing? It's more likely school's canceled. So with this in mind right here, if A happens, if something happens, if it tells you nothing about B, then they are independent. So once again, snow and school are definitely what? When you think about snow, every kid knows snow and school are definitely what? Independent or dependent? Like you would say school is what on snow? And then think about how it relates to this. You would say school is what on snow? Well, school might depend on snow, right? Does that make sense, Jesse? Like, if it snows, would that tell you nothing about school happening? Like I say, it's snowing today, it's a blizzard. Would that change the probability of school? So if it snows, would that change the probability of school happening? Like to say school is going on today or not? If it snows. Yeah, depending on location too. Yeah. Are we up north where like it snows and they're like, whatever? Are we down south where there's like a snowflake in the air and they're like, school's canceled. We don't have the snow plows down south. So there's a lot of things, right, too, that depends on school being canceled. So if I know A happens, it tells me nothing about B is going to be independent. I would say school is very dependent on snow. But let's say um, Brian makes coffee. Darren, my brother, makes coffee. If you know Brian made coffee this morning, which I didn't, should go grab some. If you know Brian made coffee, would that tell you anything about Darren making coffee? If you know Brian made coffee, would that tell you anything about Darren making coffee? So if we know Brian made coffee, exactly. I know Brian made coffee. That gives me no information on Darren making coffee. So Darren making coffee is independent of Brian making coffee. This is how, don't start thinking about the second words here, because a lot of times people will say, is that disjoint? Is that mutually exclusive? Is that dependent? I'm like, well, it's not dependent because it's independent. Dependent and independent are versus each other. Now you have to be careful because something that is dependent doesn't mean it must happen. So when we say school depends on snow, some people say to me, well, sometimes it snows and we have school. And I say, well, yeah, but we're less likely to have school if it snows. It doesn't mean if things are dependent, which that is, that if one happens, the other can't happen or will happen. So it just means it tells you information about it. It influences your idea of it happening because, okay, the probability of this happening depends on the other thing. So the probability of school happening today would depend on if it snowed last night, which is not going to snow lately. So don't think of it as, a lot of people say, well, wait a minute, it doesn't totally make it so we can't have school. And I say, well, it's somewhat dependent. Not 100% dependent, but it is dependent to a certain degree. That's what we think about when we think about dependent, independent. Now, disjoint means if one happens, the other cannot happen. And disjoint is mutually exclusive. So disjoint events are very clearly what? If one happens, the other cannot happen. So I'm asking you to blend the words here. Disjoint events are very clearly what? Because if one happens, the other can't happen, cannot happen. So disjoint events are very, very clearly what? Like they are the most this anything could be. If we're going to say, yeah, my classic examples right there. I like that, Jesse. They're very, boom, Jesse, you got it all. They're very dependent. And I like to use my classic example of your parents say to you that you are getting either a dog and maybe 6% probability, a cat, 30%, or you're getting nothing. So you're getting a dog, cat, or nothing. So with this in mind right here, with dog, cat, or nothing, what do you notice about all the probabilities right here? All these probabilities, what right here? All those probabilities, what? They add up to 100%. And your parents are like, okay, tonight we're going to go get a pet. Look, we're looking at 6 dogs, 3 cats, or you could get nothing. It's not quite the way you would do the probabilities, but we're just kind of doing the math here to say one of these things will occur. You can't get nothing and get a cat. You can't get nothing and get a dog, because obviously if you got a dog, you didn't get nothing. And your parents are not letting you get a dog and a cat. You can only get a dog or a cat. So you could say, what's the probability someone gets a dog or a cat right here? So this is if one happens, the other doesn't happen. We can use the addition rule right here because they are disjoint. They meet that condition. So what is the probability? It's very easy to see. What's the probability someone gets a dog or a cat? 90%. That's all you got to do. Now, this is weird. So this is a trick question, which we've done before. What is the probability someone gets a dog and a cat? And these are disjoint. I want to point out that these are disjoint events. What is the probability that somebody gets a dog and a cat? This is a trick question, and it's with disjoint events, and it might even say that these things are disjoint events. What is the probability someone gets a dog and a cat? And the term disjoint tells you the answer. So what is the probability someone gets a dog and a cat tonight? This is a trick question, and it would say something to you like, these are disjoint events. What is the probability someone gets a dog and a cat tonight? It's a trick question, but the Isabel, good to see you here too. Yeah, we can do one here. You cannot have that since. So, what would you put down if you had to enter something into the test? You are right, Jesse, and then we'll do that one next. Isabel, you got it? Isabella? You are correct, Jesse. So, what would you put down? 0. Yep. Because if one happens, the other can't. So, it's impossible for them both to happen at the same time. So, it's a trick question because we're telling you they are disjoint, and then we're saying, like, what's the probability they both happen? And since they are disjoint, that's impossible. So it's a trick question. You'd say, well, isn't it the multiplication rule because you said and? But remember, we said disjoint events are dependent, so they don't meet the condition needed to do the multiplication rule the traditional way. So at that point, we have to say, with our knowledge, that if it's completely disjoint, if you got a dog, you can't get a cat. So these can't happen at the same time. Exactly. So is that making sense to Jesse? You're doing a great job. We'll throw one last question on here, and then we'll do Isabella's question. Because now we say, we work at a shelter that has these probabilities. What is the probability that someone in the next 5 people, there is at least one cat adopted? Okay. We work at a shelter with the following probabilities. There's at least one problem here. We work at a shelter with the following probabilities. What is the probability in the next 5 people there is at least one cat adopted? So I think I know it. I think I know the mathematics, Jesse. I'll give it a second right here, see if you can get it for 100 points. You might need to put the equation. It might be that. That sounds about right. If you got it that quickly, amazing job. Let's see. And Jesse, you did it. Yep. You did it. That's right. So let's show the mathematics right here. We have 5 people walking in. Yup. See, these at least one problems are not so bad once you do like a whole bunch of them. You're like, okay, what is it asking? So we have 5 people walk into our shelter. And we want to say, what's the probability there's at least one cat adopted? So we need to write 2 scenarios right here. The 2 scenarios that are really going to make this make sense are, we'll take the 5, we'll bring them up here. So what are the 2 scenarios, Jesse, that you would write out? Great work. Yep. So we have the possibility that no one adopts a cat, or at least one person adopts a cat. And this is going to be the total scenario here. No one gets a cat, or at least one gets a cat. So these are complements of each other because one of these things must occur. Either no one will get a cat, or at least one person will get a cat. And the probability of no one getting a cat is the first person doesn't get a cat, and the second, and the third. It's the multiplication rule, and we have 0.7 here because that's the probability of not getting a cat. Getting a cat is a 30% probability. Not getting a cat is 70%. And there's that. And we can just copy the rest of this. We're going to abbreviate this down a little bit right here. And great work, Jesse. I was trying to write a somewhat difficult question, but you got it immediately. And there's that. Now we just algebra it. And perfect. And with the algebra, to me, it's amazing. Once you get these down, it's like, okay, exactly. And so Jesse got it. Either not getting one is nothing plus dog right there, which is another way of doing it. And there's all the mathematics right there. The final solve right here is going to be equal to the 0.831. If you get a decimal wrong, just don't worry. Let me know. But there are 2. Depends on how many decimals it says to round to. But Jesse got it right there. Perfect answer. And really great practice. Just think about trying to write questions like this. You can make up questions like this for your friends. If you notice, we kind of went through and this is the majority of the chapter, right, Jesse? I mean, what did we just take here? And then we're going to do Isabella's question. We just did the majority of the chapter in about 15, 16 minutes. I mean, that's a big overview, kind of almost speed run. I can't say this covers every little detail of the chapter, but we did the complement rule, we did the disjoint, we did multiplication, addition. So really good stuff right here. And thank you, Jesse. Really good stuff. Full page sheet review. But know how to do these things and know how to solve these problems, know how to write your sentences. And then if you think through the sentence, you can get it. And then you can solve the mathematics. And then you get the answer. With that, let's do the question. Hey. Researchers measured waist sizes. Is it on the homework or the quiz? Quiz question. Okay, here we go. Let's look at researchers measured waist sizes. Quiz. Okay, let's do it. Okay, so we have researchers measuring waist sizes right here. And the key to these problems is the notation. You have to know your notation. So any of the notation for this problem right here. What is any of the notation? So we've got 234 men had their waist size measured for a study. The waist sizes of those 234 men was 36.316. That was the mean. Important right there. And the standard deviation was 4.027. Now, I want to point out the first thing we always decide in our class is we always decide if this is a quantitative or categorical question. Now, the reason we decide this is because if it's quantitative, we'll start using equations like this right here. And if it's categorical, we'll start using equations like this right here. If you notice, there's a change in the notation such that you will be finding and looking for different things. So if you use the wrong notation, you get to the wrong answers. And this is success failure, and this is large enough n. So we need to know which way we're going with this, and they measured waist sizes. So they measured the size of someone's waist. So when you think of measuring the size of someone's waist, and if you took data on that, would that be a cat variable, categorical, like yes, no, or and it could be groups like freshmen, sophomore, junior, seniors, categorical, or would that be quantitative? And it's definitely quantitative. Great job, Jesse, right there. Quantitative because the size of your waist is how big is your waist, and that would be numeric mathematical. So it tells us we're going to be using this notation over here and using the third condition, large enough n. These are important things to know. We've already got a kind of route for going with this question. So now we get to the notation. Great job. I think Jesse's got it all right there. Now, Jesse, there's one small thing, 100 points. This is actually being used as the population size. So great job, Jesse. This is the population mean, and this is the population standard deviation. And then these are the different sample sizes and they're using. So very small, another 100 points, Jesse. That's just the smallest of things. Probably won't even matter on the test, but you could check the 10% condition here with all of these. Notice how they do much smaller samples. Yeah, no worries. The capitalization means population versus the lowercase means sample size right there. So it's weird. A lot of times we use Greek letters. Great job, Jesse. 100 points, putting all the notation in the chat. And then you can just try to remember that population mean is mu. Population standard deviation is sigma, sample size is n, and then we have here some extra stuff. Because what we are trying to find is if we were to talk to 2 men, 5 men, 10 men, 20 men, then what would we see in the data? And it's very important to know this. Let's go here to the sampling distribution applet. So with the sampling distribution applet, you will notice here we have a normal distribution. Now we are going to sample from this 2 observations. And now we get the mean of 2 randomly sampled observations from this population of individuals. Like this would be the 234 people, and then we take a sample of 2, and we take the mean. Now what we're going to be talking about is not the original mean, which we have right here. Just showed it for a second. There's the original mean, which is up here. We want the mean of the sampling distribution. But the mean of the sampling distribution, which is the lower one, is interestingly enough the same mean as the top. So this mean down here is what we are solving for when we solve for mu y bar. This is the mu. So that's mu, and then the lower one is mu y bar. Now this is sigma in this example, and this is standard deviation of y bar. So that's the standard deviation of y bar. Let me put it on the other side. That's the standard deviation of y bar right there. Now, how is this standard deviation of y bar being calculated for this example right here, Jesse? So what is the mathematics that would go into calculating that value? And it does use a capital N here, which I don't like. It should be n equals 2. So how are we getting the new standard deviation in this example, which this applet, we probably did enough simulations, but how is that standard deviation of y bar being calculated? And I guess I might show it. You're doing excellent work. We take the square root of 2. We take 5 divided by it, and there's 3.53 right there. And that is how that standard deviation is being calculated. So we could increase n right here. If you notice, the mean will stay the same, but the standard deviation gets tighter. And that's what this example is going over right here. When you look at it, it's showing you the mean is going to stay the same because the mean is always the mean. Sample size is not going to matter.
It doesn't matter!
But the standard deviation is going to get smaller by a factor of the square root of n. Now, I like to cheat a little bit here, 4.027, because we just need to put in our numbers. I was doing some extra work over there. So there's the standard deviation, and then the sample sizes, I think, were 2, 5, 10, and 20. Stand 3, and there's the values, and then I can just cheat. And I'm going to show how to get these. But to 3 decimals, I just like to make sure I get them correct, even though I have made errors doing this. If you notice, the standard deviations are getting smaller as we go for larger sample sizes. So we'll calculate one of these by hand here too, maybe like the last one. So what we would do is we would take square root of 20, and so there's square root of 20, and 4.027 divided by square root of 20, and there it is. Once again, we are just plugging in the numbers right here of sigma. Sigma's right here, 4.027 divided by square root, and we're using the last number there, 20. So the standard deviation, hey, Sheena, good to see you here. What's up? Just saw you in the chat, 100 points. We're just plugging in the new sample sizes. Did Newbot not give out those points? There we go. So the sample size is just increasing right there, and that is making a smaller standard deviation. Now it's going to show us a simulation right here of what's going on. And if you notice, it is a little skewed to the right to begin with, and then it starts to become more normal. And there's the theoretical or the simulated values, which are close to our theoretical values. So the simulation is not always going to be exact. Reason being is, and like I can do my own simulation over here. Like let's do from a random normal data set, we'll sample 20 observations where the mean is equal to 70 inches tall with a standard deviation of 3. I'm actually going to change this to 100. Now, what's interesting is we do this and we run the data. And let's see right here. Let's go the mean of that data. Whoops. The mean of that data and the standard deviation of that data. Now, the mean is going to be about 70, and the standard deviation is going to be about 0.3. There it is. Oh, I didn't take the... I need to do the mean of... need to do a simulation. I have to go to class. Awesome. I'm having a little bit of fun right here. 10,000 trials of this. And then let's go here. Data. Store the data of this. And then when we run it right here, let's go to output. Store the output as a blank vector. This is the fun. I like doing this kind of stuff. Good practice. And so now output position 1, because that'll be the first thing it goes through, is going to be the mean of the data, because that's what we're finding. Okay, so now when we run this right here, I got my level. Nice, Jesse, another 100 points. Get to your level right there. mean of data and standard deviation of data. I would expect like a 474 student to be able to do this. And what am I doing wrong? Oh, output. Haha. Oops. There we go. There's the 0.3. And this is a simulation. So what I wanted to point out right here is, if you notice, I theoretically thought it'd be around 0.3, but it's not exactly 0.3 every time, but theoretically it should be around 0.3. So that's why when they do their simulated values over here, which they're basically doing what I'm doing, their simulated values are going to be close to our values, our theoretical values, but they might not be exact. Via theory, I can tell you the answer for what the standard deviation and mean should be. Like if I change this right here to, let's say, 8, and I change this to 16, now the standard deviation should be 2. So this should be still the mean, because the mean stays the same. And then this is the original standard deviation divided by the square root of n. Square root of n is 16, which is square root of 16 is 4. 8 divided by 4 is 2. So that's 8 divided by square root of 16, which is equal to 2. So we run the simulation again, and what do we see? 70 and 2. And notice how it's not exactly 2, and if you keep rerunning it, you might see a little variation around 2, like 1.99, and that's what we're seeing right here in this example, where they're simulating it and getting values close to what we get. It looks like they also didn't do as high amount of simulations as I did. They might have just done like 100. If you only do 100 simulations, you'll get values that are further away. So if you notice right here, I was doing like a lot of simulations. You notice that takes much longer. And now it's going to be super duper close to 2 because I did, 10 million simulations right there. Which is really neat to think we can do stuff like that. And see, now it's very, very close. 1.99999 and 69.9999. Compare that to the simulation that did not have the law of large numbers, another review concept. Yep. So those theoretical values are reasonably close. And looking at the histograms of what sample size would you feel comfortable using it? A sample size of 5. Ooh, since this is the smallest sample size at which they are unimodal and symmetric, that's a tough question right there. It could be 10, but I think they're saying 5. It's pretty unimodal and symmetric at 5, and I think they might even have cheated and make that look nice. Why? Well, the reason is this is the large enough n condition right here. The large enough n condition states the more the original distribution, sometimes called the parent population, is skewed, the larger n needs to be. Now, you could also say the less normal it is. So we like to use numbers 1, 25, 100, and 500 if it's very, very skewed. You'll see 1, 25, and 100 in the notes, but we would want to know what is the original shape. And that's what they're pointing to in this question when they say, since it's not very skewed to begin with, right here, because what about the shape? The distribution of weight is unimodal and symmetric. The distribution of weight is unimodal and symmetric, so the same mean is for even, yes, correct. So since the original distribution is pretty unimodal and somewhat symmetric, it's not going to take a very large sample. And that should do it. We should get everything right. There we go. And you can see it right here with a sample size of 2, the lower distribution of means is unimodal and symmetric. But if I had a very skewed distribution, even more skewed than that, something like this right here, this is a very, very skewed. If you do a sample size of 2, it's not normal. You need to go up to much higher sample sizes, and we might still see a little skew over here. But for very, very skewed distributions, you need much higher sample sizes. So that's very important right there. Really good review. What other questions are there? Let's see. Sheena, do you have any questions? We did some review today. What other questions? The review videos here are going to be very important. Very important. Highly important review videos. Oh. Highly suggest watching the review videos. Might end a little bit early here today. Next week will be a big week. We do have, maybe I'll post this. We did do the full quiz. And so remember, make sure to be here. We've done the full quiz. We've been doing different things during different office hours. So we might end here a little bit early, but we'll be back. Might do some office hours tomorrow. You never know. Till then, bye for now, everyone. Bye.